All right, so we're going to do another proof. So this one, we're going to, our theorem is that if f of n equals, let's see, 1, if n equals 1, and f of n minus 1 plus k for n greater than 1, then f of n is equal to k times n minus k minus 1. Okay, so our proof by mathematical induction on n. Our basis, remember we're going to test this for the case where n equals 1. So we must show that so we're doing it for 1. So we're going to show that f of n, let's do it for 2. F of n is equal to k times n minus k minus 1. So our basis, we're going to say n is equal to 2. Okay, so let's try that. So we're going to say for n equals 2, then f of 2 minus 1 plus k. So this is we're taking right here, this piece right here. I'm going to say, does that equal this? Right, so this is my closed form, and this is my function. And so I'm taking my function first and saying, does that equal k times 2 minus 2 minus 1? Minus k minus 1, that's a k. Okay, so what is the function for 2 minus 1? That's the function for 1 plus k. And does that equal k times 2? So let's say that's 2k minus k, and we're going to distribute that, so plus 1. Okay, well, so what is f of 1? Well, up here, when n equals 1, f of 1 is equal to 1. So I'm going to plug that in. So 1 plus k, does that equal, so 2k minus k is k plus 1. So it works for k, for n equals 2. Okay, now we're going to go on to do our induction step. So we have to say our induction hypothesis. We're going to assume that this function is equal to the closed form. So k times n minus k minus 1. And so for our induction step, we must show that f of n plus 1 is equal to k, and I'm just plugging in here n plus 1 minus k minus 1. So that's what we're going to show. So what we want to do here then is we're going to use our definition for our function right here. So I'm going to use this definition right here to plug in for our function down here. So I'm going to say 2, or sorry, it's not 2, it's k. K times n plus 1 minus k minus 1, right? I just plugged, this comes from this right here. So actually I did that wrong. Let me erase that. So I want to be using this right here. So I'm going to say right here, I want to use this right here. So I'm going to plug that in. So f of n minus 1. So I'm going to say n plus 1, right? I'm substituting in n plus 1 for n, and then minus 1 plus k does it equal k times n plus 1 minus k minus 1? Does that equal? So what is f of n plus 1 minus 1? Well, that's just f of n plus k. Does it equal k times n plus 1 minus k minus 1? Okay, well, f of n we know because we assumed this. We can take this as my assumption, so I can plug that in for f of n. So that's going to be k times n minus k minus 1. So that's I plugged in for f of n plus k. Does that equal k times n plus 1 minus k minus 1? Well, let's see. So I've got a k here and a k here, so I'm going to factor. So I'm going to say k, and then I've got an n and a 1 there, n plus 1 minus k minus 1. Does it equal k times n minus 1, or n plus 1, minus k minus 1? And it does. They're both, this side is equal to that side. So we did it.